each icon. To view the agenda and see the sessions and demos for today, click on the Call to Action icon. Enjoy the conference.
Thank you so much, Darvila. Hello and welcome to everyone. This is Lalan Mishra. I work here for Qualcomm, and today's DevCon presentation on RFFE is focused on RFFE 3.0, and we'll take a dig at it from the systems architecture point of view. So let's get going. So before I proceed further, I would like to thank some of my colleagues who have done their contribution in the preparation of this deck. Jim Ross from Skyworks, Vic Wilkerson from Corvo, and Werner Hein formerly from Intel. The agenda is straightforward. We'll first introduce RFFE. We'll take a note at a few historical development, how RFFE came to be. And then we'll talk 5G and some of the new requirements that it is bringing on the table, and how the new requirements that we have integrated into RFFE 3.0, what those new features are. Primarily, they are additional extended triggers, time trigger, and mappable triggers. At the end of the presentation, I'll summarize everything and open the floor for any questions that you might have. So in terms of the introduction of MIPI RFFE, 10 years back, before 2010, when the first spec of RFFE was released, the RF front end was a complex story. There was no common interface to control the RF front end components. People were using large number of I/O pins, and also the interfaces to control them was not uniform. As a result, there was complexity in hardware architecture as well as software. So a solution was needed. That's when MIPI stepped in, and the RFFE 1.0 came into existence. The release introduced a bus in terms of just 2 pins, one clock line and another data line, supporting one master and multiple slaves. Up to 15 slaves could be supported on one common bus with one master, and it can also have a secondary master, if you will. So for the past 10 years that MIPI RFFE has been in existence, it has fueled a lot of devices that require wireless communication. And if you just count the sheer number of RF front-end components, which currently is using MIPI RFFE, that number would definitely run into billions. And here you can see that the area where, on this diagram, where the RF front-end component comes in, primarily these are the components of the types like RF switches, mixers, or ELNAs or PAs. These are at the very front of the RF device, and that's why they're called RF front-end devices. And they're typically controlled by the modem or the RFIC. So the RFFE bus typically exists between the RF front-end component and these two main chips that you have in your device. Now, if we take a look at the evolution, so when the first revision of RFFE, first spec was released back in 2010, it contained just the bare minimum set of features, the bare minimum features to enable the RF front-end control. But then, over a period of time, there was evolution, and with 2.0, a number of new features were announced. The most noticeably was the increase in the speed and also synchronous read and additional features. 2.1 saw some additional features come into picture. The most important ones, some of them which are listed down here, are like mask write, extended reach, then we have the master context transfer. These features enabled different capabilities which were earlier not possible. I will not spend time on these features because I expect that you can go and read about these features in the spec, but these were the new features added. The focus today is primarily on what we have in RFFE 3.0, and that is what appears in the very last column here. So these features driven by the 5G requirements are additional number of extended triggers that we added, time trigger, and then finally the mappable triggers. So first, let us see where the requirement is really coming from. So it is all set into this, fast developing 5G era that we are in now already. So 5G has pushed the envelope, the KPIs in all directions on all parameters that we can talk about. And the impact of this has been that it requires the control timing that you have to have for the RF front-end components. The latency requirement has reduced further down. So even though, for example, the RFFE 1.0 was just happy with 26 megahertz of operation, we increased the speed, as you know, as we saw in the previous table, to 52 megahertz. But with 5G type of requirement, even though the bus speed is still at 52 megahertz, some of the control timing or the control requirements, those timing restrictions have become more stringent. And that's where some solution was needed and has been the primary focus of RFFE 3.0. So if we try to see the bulk of RFFE 3.0 enhancement that we have here, they could be put inside 3 buckets. So the first one is additional number of triggers. In 2.1, RFFE 2.1, we had introduced 8 extended triggers, giving a total of 11 triggers available, maximally available on any RFFE devices. Now, seems like that with RFFE, with 5G requirements, those numbers need to be, extended further. And with additional extended triggers, we have added 7 more triggers in the group. So giving a total of 15 extended triggers. Then the next feature, which is of very high importance, is actually the time trigger. So time trigger, you will see the latency aspect that we talked about coming from the 5G control requirement meets a very, very special purpose. And you will see that it reduces latency. How it does so, we'll come to that in a moment. And then the third one is actually the mapping of triggers. So before RFFE 3.0, the world of triggers on RFFE was all hardened trigger. Like you cannot change the trigger association, dynamically. And some of these dynamic aspects of trigger configuration is required because of the complex RF front end in 5G devices. And so therefore, these 3 additional enhancements that we have make the 3 key pillars of RFFE 3.0 and are the most important features that you require to have for your 5G capable devices. So let's go to the next page. Before we proceed further, I'm sure most of you know how the RFFE trigger really works, but it is a good idea to give a refresher here. So let's see what does it really do. So in this diagram, we have conceptually shown that on the timeline, you can imagine that you have some devices inside some front-end component. It could be your PA or ELNA, where you need to set some gain as an example. And when you want to synchronize it with some other setting, that's when trigger comes into picture. So RFFE being a serial bus, when you send the data, which these elements have to use, that data will arrive at these devices sequentially because the nature of the bus is not parallel, but it is a serial transmission of data. So as they come serially, the data is held in some shadow register temporarily. But once all of them have been sent out to different devices, then you want to fire them or trigger them. And to do so, you need to send another command sequence, which is appearing here on this timeline as these smaller packets that you see here. So as these triggers arrive, all that they do is they move the data from the shadow register that they were currently staying at, and then they move them to the actual control element. And once that happens, the actual trigger is fired. It is kind of equivalent of coming to an airport earlier, staying in the waiting area, and once the boarding starts, you get inside the airplane. So you send the data early enough, and then once you fire, the data is moved into the actual control location of your desired purpose. That's what trigger really is. So now let's proceed further and see that the trigger evolution across all these RFFE specs that we have now over the past 10 years, how that itself has evolved. So in the first release, we had only 3 triggers. Then with RFFE 2.1, we included 8 more triggers. And now with RFFE 3.0, we have extended it by 7 more triggers. But now there is more to that. Just now, beyond just adding simple extended triggers, there is much more to that. So what are those additional things? So this is what we have summarized here. So these 8 plus 7 triggers that you see here in this diagram, they are capable of supporting either the time trigger function or the mappable trigger functions. But these 2 features are not available to these 3 triggers, 0, 1, and 2 that you see here. These are available only for these 15 triggers that we see here in this diagram. Now, one thing I must clarify here, that you are not required to implement all these 15 extended triggers in any of your device to call it RFFE 3.0 compliant. This feature itself is optional by nature, and your implementation would be pretty much decided by what your system requirement is and how many triggers you need, which triggers should have time trigger function supported, mappable trigger feature supported, etc. So all those things will be driven by your system's requirement. Now, the key question here now is that what problem does time trigger attempt to solve here? So we saw this diagram on an earlier page, but here let's revisit it from the timing point of view. So I explained that you send the control data through a command sequence. The data gets loaded into shadow registers, is just waiting there, and then you have to send another set of command sequence to actually move the data from the shadow register to the actual control register location. Now, to send this control sequence that you have here, that will take some finite amount of time. And you can see here that how much latency it is going to take if you are sending, because minimally, if you use a register write type of command sequence, you're looking for 25 clock cycles. So there is no way to send or trigger your actual trigger by, in other words, to move this data from the shadow register to actual control element without having at least a delay of 25 clock cycles. There is simply it is not possible. But then, like I said, that this 25 cycle itself is going to require some latency, which is shown here. And our goal in the 5G world is required to be in the ballpark of half a microsecond or less to be more effective. But then please keep in mind that this is precisely or only if you consider that you send the command sequence to load the register and then move from the shadow register. You have to also factor in other variables. For example, the bus may be available for other type of data transmission. So which means that the bus is not always available to you, and therefore more latency could be added. So the latency, you can clearly appreciate here that is a big factor, and there is a much bigger variability associated if we don't change the architecture. That's where time trigger really comes into help and provides a very good solution to help address this issue. And we'll see what exactly it does and how much time do we really reduce. For now, for the comparison purposes, I would ask you to keep, even if we discard other variable, just keep 25 clock cycles that you have minimum latency in place, and that is what we want to reduce. So here on this chart, you see that based on the different types of command sequences, how the trigger firing latency could vary. And here we have compared across register write, extended register write long, and extended register write. So you can see that, of course, because these type of command sequences require different length, primarily because for register write, for the extended register write, you require 8 bit of data, register address location. For extended register write long, you need 2 bytes to indicate the address. So that is what adds to this increased latency depending on the different types of command sequence that you may want to use. So this is another angle to keep in mind, that how the latency adds up very quickly based on what kind of command sequence you use to actually enable your trigger. So now what happens is that operationally, first, before we go further, let's try to put things in order and see that how does time trigger really come into picture. So far what we have said is that you send the control data. The control data is occupied or is stored temporarily in a shadow register. And then when you send another command sequence to trigger it, what it does is it moves the data from the shadow register location to your actual control register location, which is which you may implement in the UDR region. Now, what we want is that we want to eliminate the role of this command sequence, which is really required to set these trigger bits to make this movement happen. So time trigger, what it does is it implements a bunch of counters. And these counters actually are loaded. So when you want to enable this trigger operation through time trigger, the first thing you'll do is you'll load these counters. And then the role is reduced to just reducing these counters so that it reaches 0. And when it reaches 0, it will do the same job, meaning it will fire the trigger. And the data will move from the shadow register to the actual control location. So in summary, therefore, the time trigger is nothing but a set of counters based on how many of them you have implemented. And these counters have to count down. The countdown operation is actually done by the clock ticks which are available on S clock. So it is important to know that the MIPI specification does not require you to have a local oscillator on the slave side. The clock is required to come over S clock of RFFE bus itself. And then it is counting down. Once it is reaching at a value of 0, the data will move and you will have the trigger fired. That's the high-level concept. Now, if we come and look at this diagram to highlight the point that how you can maintain a latency of less than 25 clock cycles between two trigger firing, that is what is illustrated here in this diagram. So what it shows is that, for simplicity, we have two packets here. So the blue and the red. That's what we send the value to be loaded into two counters, for example. As the value gets loaded, as soon as it is loaded, the subsequent S clock ticks, which are coming on the RFFE bus, they decrement the counter. And you can see that this decrement, because these were, the loading was basically subsequent, one after another one, you can see the firing of these two triggers are only 1 clock cycle apart, which actually is not possible with the traditional approach of utilizing a command sequence. So essentially, you have reduced a latency of 25 clock cycles minimum to 1 clock cycle. And that is a big plus point of time trigger operation. And it can help you immensely where you are in a time crunch, meaning that you don't have sufficient time to do this type of synchronized triggering. And time trigger can therefore be helpful right there. So proceeding further, now, so we saw two things so far. We saw that we added extended triggers, 7 more of them. So adding extended trigger was simple and straightforward. You just enable more and more of them. We saw what time trigger is and how it really works. Now let's talk about the mappable trigger and how do they really help. So backward to RFFE 2.1 or previous generation, trigger was hardened, meaning that the association of your shadow register to the control element was, of course, firm. It still is firm, even in RFFE 3.0. But what has changed in 3.0 is that which trigger is going to cause the movement of data from the shadow register to the actual control element. In early generation of RFFE specification, this trigger number was, the association of the trigger number was actually fixed. So you cannot change it dynamically. But now it is dynamic, meaning that you can associate this pair of shadow register and control element register to any trigger out of those 50, not counting the first 3 triggers. And that is what is the beauty of this mappable trigger architecture. How does it help you? Because in the complex 5G RF frontend, you may want to reuse many components, and that requires remapping. For complex MIMO configurations, you do require such mapping to be reconfigured, and that is where the mappable trigger comes into picture. It also alleviates a lot of pressure from system designer, hardware designers who have to assign what trigger number is associated with a particular control element. You are no more required to have all those, tracking in your design cycle. You can rely effectively on this mappable trigger. So if we now take an example here in this diagram, you can see that the same shadow register and control element has been associated with 3 different trigger numbers. That is what we have shown here in this diagram. So now, out of these 15 triggers that we have here, of course, to manage that association in any possible way that we want to have, we need at least 4 bits to do this muxing operation. So what we have, what we call here is that you need these 4 index bits to change the mapping of these triggers to any of the shadow register and control element association. And the good thing is that these 4 index bits that you have are not required to be in the MIPI reserved area, and you are free to implement them in whichever way you want in the UDR space. It could be in the lower region or the upper region based on your device, UDR register availability. You are free to choose a location for them. But essentially what it is that you have a mux and you need 4 bits to control the mux to have this operation done. That is all about mappable trigger. The concept is simple, but the effectivity or the effectiveness of this concept is very powerful in connection with 5G. Now, let's try to put everything in context and bring everything together here. So now what you see here is that the older technology was only these 2 registers you can see in terms of trigger operation. So you had the trigger and you had this, the mask bits. But whenever the mask bit is something that you set only one time and then you forget about it typically. And you had to supply these trigger bits to fire a particular trigger. Now, what we said that with time trigger, you have these counters which actually do the same job, and they set these bits accordingly to move them data from the shadow register to the actual control location, or in other words, firing the trigger. So this is where the time trigger combined with the traditional trigger mechanism. Now, on top of it, we add this mux, and these muxes are nothing but what we just explained in the mappable trigger. So the overall architecture of the enhancement, trigger-related enhancements that we have done in RFFE 3.0 is right here depicted on this diagram. And it's very clear. Very easy to understand, the architecture is simple, and you can appreciate that implementing all this thing is not going to be very demanding in terms of device complexity. So in terms, a few words about the trigger register utilization. What we have done is to make sure that most of the time, if you have time trigger, you would be loading those counters, and you want minimum time is spent to load those registers. So therefore, they are located in the lower register region. So if you want, you can access them by register write operation. You can, of course, use the other datagrams if you have to load a bunch of them in a sequence, and therefore, they are in the lower register region to minimize the latency. Now, the muxes, the index bits that we talked about for mappable trigger, they are left on the designer's choice or the architect's choice, whether it should be in the UDR region, lower UDR region, or upper UDR region. Both are available to you. Whichever way works for you, you should implement it there. So all these things are to ensure that your latency remains as minimum as possible for time trigger, and you have maximum flexibility to implement mappable trigger. Now we come to the summary. So let me summarize everything here. What we talked was that the latest version of RFFE is RFFE 3.0, released in April of this year. And it has introduced 3 key architectural enhancements. We have added 7 more extended triggers. We have added time trigger function. And we have also added the mappable trigger architecture that allows flexibility of mapping the trigger whichever way you want or require in your system. Now, the RFFE 3.0 follows the same electrical spec as applicable to the RFFE 2.1, which means that you don't have to worry about the clock speed or anything. It is exactly the same electrical spec, no changes there. So as at the work group level, now we are focusing more on the next generation and see that what features we should incorporate into the new version of RFFE. So those of you who are participating at MIPI RFFE, we would like to hear your ideas, the problems, and we can discuss as a work group how to solve them. So on that note, I would stop here, and I'll be glad to take any question that you might have. So thank you for your time.
Thanks, Lalan. Appreciate that. I encourage questions to come in via the Q&A window. And would like to start off. We have a few questions here. While a time trigger counter has not reached 0 in its countdown sequence, can the RFFE master launch a new CS? And if so, then as a system designer, what system level aspects should one keep in mind?
Thank you, Dervla. That's a great question. So as we know, all that is needed by the time trigger operation to reach trigger point is the S clock availability. So yes, a new CS can be started by the RFFE master. Each command sequence hides 2 clock cycles due to the launch of SSC, as we know. So though a few of such occurrences of SCs or CS can have no adverse effect on the real-time aspects of the time trigger, considering the S clock frequency in use and the CS repetition, real-time behavior may get impacted. I'm emphasizing on the word may get impacted. So system designer needs to keep this particular thing in mind. Otherwise, you will not see any effect whatsoever. Thank you.
Thanks, Lalan. Just looking at the Q&A pane, I do see there's some more coming in. I understand the ability of time trigger to maintain previously unachievable inter-trigger firing latency. Can the same be achieved between a CS-based trigger and time trigger? And if so, then what are the key points to keep in mind?
Right, another good question. So now we are talking about mixing the 2 types of triggers and maintaining some latency of choice that we have. So the brief answer is yes. One would need to keep in mind that the absolute time delta between the firing of the 2 triggers and the issue of the CS-based firing and counter-based loading should be done accordingly. As long as you take care of this aspect, you can maintain a minimal separation in the time domain between the 2 types of trigger firing. Thank you.
Thank you. Another question. You mentioned that for Mappable Trigger, the index bits are to be allocated in the UDR space. Should one have a preference of the register location in the UDR space for this purpose? What factors should one consider to make this decision?
Yeah, I would say another good question. So as you know, depending on which location you have picked for certain registry access, you may want to use one command over the other. Keeping these index bits will help you in the lower region if you have to change them very frequently and you want to minimize the overall latency on the bus. But if such a requirement is not there, you may want to keep them in the upper memory region. So yes, please go ahead according to your system requirements, how frequently you have to use them, and accordingly you can pick the location either in the lower UDR or in the upper UDR. Thank you.
Thanks, Lalan. I encourage more questions through the Q&A window. Currently, I do not see any more, so would encourage the attendees to go to the Engagement Hub and check out our upcoming session. This is a closing session that will close out our day 2. Meanwhile, just waiting to see if there's any other further questions from the audience, Lalan.
Okay.
Okay, I don't see any further questions, but thank you again. That was a great presentation, and thanks to the audience for tuning in and posing those questions. So without further ado, we'll transition. Thanks. We will transition over to our closing session, so stay tuned. Thank you.
Bye-bye.